We have one more thing to talk about in exponential functions in compound interest, and I'm just going to jump right into the example, and that is a comparison. If we have an investment that earns 10% that's compounded quarterly, or we have a second choice of an investment that's 9.9% compounded monthly, or we have a third choice of an investment that earns 9.9% compounded continuously, which one of these is actually going to give us our better bang for our buck? Okay. Well, if we look at just each one of them in general terms, 10% is the best interest rate, but it is compounded the least amount of times. 9.9% is the worst interest rate, but it's compounded continuously. So even though we have a lower interest rate, the number of times it's compounded could actually come out to be more than what our initial was. And then, of course, we have something in between. We have an in-between interest rate, and we have an in-between number of times it's compounded. So we want to figure out how do each of these compare with each other. Okay, well, the first thing that we're going to do is we are going to let time equal 1 because it's going to be easy to compare each of these after the end of each year. So I'm going to let time equal 1 for both of these equations. So we can just substitute 1 in for t, leaving us this here. And now we want to think about what are we actually comparing. We're going to compare the amounts at the end of the year versus the amounts that we have at the beginning of the year. So in both instances, we're looking at the exact same principle. So we can actually almost ignore the initial principle here if we're just comparing at the beginning and at the end of the year. So basically, at the end of the year, we're going to have this information here. 1 plus r over k to the k value. And at the beginning of the year, we know we're just going to have our initial investment. And so our initial investment is going to be 1 times the amount that we're putting in, hence just 1. Now, I can do the same thing over here on the right, but basically what this leads down to is our effective interest rate, where it's figured as 1 plus our same things here, r over k, to the k minus 1. So this is basically the amount at the end of the year minus the amount that you have at the beginning of the year. That's going to give you your effective interest rate. So now we can take these formulas and we can actually apply them to this example. So I have my effective interest rates here. All you need to do is plug in the numbers where appropriate, and then we can compare our interest rates for each of these situations. So I suggest that you pause the video and you figure out which one of these would be the better bang for your buck. Okay, the first two I'm going to need to plug into the first formula because that's an actual number of times it's compounded a year. And then the last one I need to plug into my continuous formula here. So let's start with the first one. And this R stands for here the nominal rate. In the first one, our nominal rate is 1 plus, my rate was 10% compounded quarterly. So that's my nominal rate for my first example. My nominal rate for my second example is 1 plus my interest rate of 0.0995 compounded monthly. And then my third example, my nominal rate, is e to my rate, 0.099 minus 1. So all I need to do is type these in my calculators to figure out which one of these gives me my best nominal rate. So let's pull up my calculator here. My first one is 1 plus 0.1 divided by 4 to the 4th power minus 1. That gives us a nominal rate of 0.1038. My second nominal rate is 1 plus 0.0995 divided by 12 to the 12th power minus 1. That gives us a nominal rate of 0.1042. So our second one is actually a better deal than our first one. So let me write down these values here. And now let me look at my continuous one. And so that calculation is e to the 0.099 minus 1. And so the nominal weight there is 0.1041 if I were to round to the fourth decimal place. So we see our last choice is just barely a little bit below our second choice, but that tells us that our second choice is actually going to give us our best bang for our buck. So if we wanted to choose which one of these, then we should invest the 9.95%, which is compounded monthly. And so that's going to give us the largest amount of money in the long run. And so at this point, we've reviewed everything that we need to know about exponential functions and compound interest and anything related to these two.